This particular homework assignment, my hope is that it takes you about 30 minutes to do. Okay, it's not a very intense one, but you will want your calculator by your side. Definitely you can do it now without having heard the lecture either today or on Tuesday. Like the instructions for how to do it are a part and parcel of the homework itself. I am encouraging you to get homework 6 out of the way so that then for this class purposes, you can focus on completing your independent research project. And for some of you that is finishing data collection tomorrow on Friday, your graph has sprouted, Carl. I'm very excited. And it's sprouted in a way that makes sense, I think. So it looks pretty good. I think that was the last cross your finger component for anybody's project. Will Carl's grass grow in the time frame that we've given it to grow? So that's good. The last Friday of class. So tomorrow is going to be Independent Research Day for lab. Come if you need to complete something, definitely. Also, if you want to talk to me about writing up your research project or analyzing your results, like I'm there, you can come talk to me. If you're like, how do I handle this? What am I supposed to do next? Doing the project is one thing. For some of you now, you're encountering data analysis. And so that's also something that we are happy to talk with you about during that time period. And that is driving us towards then on December 6th, which I think is the last day of class, the last lab day. I'm going to ask you to do a presentation of your independent research project to us as a group. We'll sit in lab and you can present to us. That presentation can be as formal as having some slides in a PowerPoint presentation, and you put some graphs up there for us, and some pictures of your experimental setup, and you tell us why it's important with slides and pictures that you share with us. Or you can sit there and just tell us what happened, and you can show us your graphs that you have printed out for your research paper. Okay, like I'm very open on the format of how you want to present to us. If you're like, oh my God, public speaking makes me break out in hives, like videotape yourself the day before and we'll play your video in class. Okay, you don't actually have to talk to us if you don't want to. That's okay. But the idea is that you know intimately what you did for your research project. I have a very, very good understanding of it. Nobody else in class does. And they're curious. They want to know what you did. They want to ask you questions about it. And hopefully those questions can help you to write a better report. They may encourage you to change small things or do other things about your report. And so right now I have the report as being due at midnight on Friday, December 6th. And again, I'll hand you that rubric tomorrow. I'll probably put it online this afternoon. As to what I'm looking for in the report. That presentation Friday morning is like a fifth of your report grid. Okay, it's like there's 40 points possible on the report, and like 8 of them come from that presentation class. Feel good? Or at least you have an understanding of what we're doing. Okay. It's important that you understand my expectations. Otherwise, how can you meet them? That's where we are. All right, cool. All right, and that's kind of it for the semester. We are talking about communities. We'll see how far into and in depth into communities that we get. We're definitely today talking about how communities are quantified and how they're structured. And we're then going to move into how communities change over time and the flow of energy within communities, which are those are our last big topics for class. And again, we'll see how far into the material we get in the 4 remaining classes that we have together. Okay. All right, so our topics today are community structure and dynamics, and we are going to pick up where we left off on Tuesday in talking about describing communities. So turn to your neighbor and see if you can differentiate with them the difference between species richness and species evenness. Okay. What are those two things, and how then are they different from each other?
Right. Species richness. The evenness is, I think, is that
it's like they're evenly kind of distributed.
Yep.
And I guess richness is just the amount of different species there are.
Yeah. Like yeah. How was your day?
I'm pretty good.
I saw my exam score, it's like, it's terrible.
Yeah, right now I'm just looking for something that I misplaced. I have too many loose papers in my hand.
What are you missing?
It's something she gave to us. She gave us an opportunity to get 10 extra points on the exam if we did something completely right. I just don't know where I put the paper. But she gave me yesterday.
Okay, what is species richness? Capital X. Good, the amount of species that you have. Do you have 10 different species? Do you have 100? Is there one thing here? How is that different from species evenness?
So in species even, you want more like 30, 30, 30, rather than like.
She gave it to us
Good.
more
yesterday when we were
spread
viewing.
out rather than kind of
That's what we did on the exam.
Good. Evenness
You can
is
always
how
look at it on the
individuals in the community are distributed across
I know,
the
but I just want to make sure because I
Are
wrote
there
some
lots
on
of
it.
individuals in one species and few in the rest? We call that uneven or skewed, or are they equitably, evenly distributed across the ecosystem? And we tend to view even distribution as more diverse. That again, the opposite of diversity then is species dominance. And so what are 3 ways that a species can be dominant in a community?
dominant population.
Good, in abundance. Yeah.
How much biomass they have.
Good, how much biomass they actually occupy. What was the third one? The last one we talked about right here.
They take the development of resources.
No, I would kind of clump that in with biomass. So like if you, we tend to with people else, that if you have the most biomass, you're consuming the most nutrients and sunlight and water in the ecosystem, the most calories. What is the other one that we can quantify or characterize dominance based on? Think about alligators in the Everglades, sea otters in the California forest. Sea otters eat urchins, and that lets the kelp grow. If there are urchins, they eat kelp, and there's no kelp.
There are no
But
predators?
there's kind of a keystone species.
Keystone species, good, because they're functionally dominant. If they're present, even though they might be rare and not very abundant, if they have a huge impact functionally on their ecosystem, they can be a dominant species. So again, the sea otter, the killer whale, the American alligator, the elephant, as we talked about it on the African grassland, these are not very abundant. They don't compose a lot of the biomass of the ecosystem, but they're the thing that defines that ecosystem. That's either there or it's not. Their presence absence determines what type of ecosystem develops and diversity of other organisms. So abundance, biomass, and function are the dominance kind of categories. Okay, putting together species richness and species evenness is the way that we quantify and characterize communities. And we can do that mathematically in a, you can talk about a community, you can show pictures of a community. We know we can recognize biodiversity when we see it. How then do we actually compare communities when it comes to biodiversity? You need something that's unbiased, that is less of a human perspective in it. And so we can calculate that with some mathematical equations, the diversity of an ecosystem. And we call them diversity indices. So in comparing one community to another for biodiversity and community composition, we tend to use these standards of mathematical equations to say which is more diverse. And they take into account not only species richness, but also species evenness. In there, I'm going to tell you about 2 of these different systems, and you'll work with both of them then on homework 6. It's a plug and chug as far as once you know what the equation components are, a little bit like life tables, you can carry it through any operation. Each ecologist tends to have their own particular one that they use, whether it's the Simpson's Index of Diversity or the Shannon-Weiner Index. They're calculated just a little differently, and they're going to tell you slightly different things as a result of that underlying math. Individual areas of ecology will always report one or the other. Good ecologists calculate them both and will report both indices. And again, hopefully in calculating both, you see the same trends as you're comparing. But the purpose of these diversity indices is really to allow us to compare disparate communities. How are you going to compare the grassland ecosystem before and after fire? You can do it on species richness, but evenness might be important too. How do you actually quantify those differences with these diversities? Okay, so let's talk about the Simpson's Index first, and then we'll talk about the calculation for the Shannon-Weiner Index. And again, sometimes we call it just the Shannon Index of Diversity. The Simpson's Index of Diversity is calculated as 1 minus capital italicized D, where D is called the Simpson's Index. And so once you've calculated D, which we've already talked about as a measure of dominance, in the reverse of it, 1 minus this dominance calculation is diversity, how diverse your ecosystem is. And what it's actually quantifying is the probability that 2 randomly selected individuals in the community will be the same species. And so if you have very low diversity, you would have a high probability of pulling 2 individuals of the same species out of your sample. And that means that 1 minus that probability is going to be very low, close to here. Okay, so like if this reverse, I do everything like reverse what you think it would be in ecology. I realized that this semester. We calculate D by summing all of the squares of the relative abundances of your species. Okay, so it takes into account evenness, the relative abundance, P sub I. We square all those, and then we add them together. And that gives you D, and then you subtract that from 1. The values here tend to range from 0 to 1 for the Simpson's Index of Diversity. And the closer you are to 0, the less diversity there is. And again, this is the understanding that if you have a high probability of selecting 2 individuals of the same species from the community, you have low diversity. Okay, and so your 1 minus D here will be a very tiny number because you had a high probability. The closer you are to 1, the smaller these additions are, the greater the diversity in the community, the smaller these little percentages are. Relatively. And so again, we're weighting this towards more even community we're characterizing as more diverse. The way that we make these assessments, the way that we get the data that goes into the diversity indices is to do transects and quadret surveys of what's actually out there in the ecosystem. And again, wildlife cameras, drone footage, photographic images are a way that we can expand and more accurately do these space system surveys in order to more accurately calculate these diversity indices. Okay. The Shannon Index, then, we often abbreviate capital italicized H. It's also measuring species richness and evenness, but the calculation here is a little bit different. But the outcome is going to be the same. Again, the higher the value of this calculation, the more diverse it is, just like closer to 1, the higher the number, the more diverse the ecosystem is. These numbers, though, based on this calculation, can range from 0 all the way up to a much higher number. And it is somewhat dependent upon your species richness as to how high this value can get. The calculation for the Shannon-Weiner Index of Diversity is that H is equal to the negative sum of all of the relative abundances times the natural log of those relative abundances. And so for each species, you figure out its relative abundance. You multiply that by the natural log of its relative abundance. and then you add all those together. And it's usually a negative number, so we take the negative of it, make it all positive and something that we can relate to. And again, the minimum value is 0, the ln of 1. If you had 1 species in your community, the relative abundance would be 1 times 0. The natural log of 1 would give you 0 for your diversity indices, indicating no diversity because you have 1 species there. The max value then can be the ln of your species richness. So again, it is dependent upon species richness. For this reason, the Shannon-Weiner index is sometimes not used as frequently because depending on the community and species richness, you can get radically different numbers as a result. So again, it works best for communities in comparison that have similar species richness. Okay. This is going through an example of the Shannon index calculation. We have our number of individuals. We find out the total number of individuals, capital N here. Their relative abundance, the P sub I, is going to be the individual species abundance divided by total abundance for the community. You get that number. You take the negative log of it. You then multiply those two things together, 0.45, 0.52 times negative 0.65 for each of these, and then you add them all together and you take the negative. Again, it's complex and kind of carrying it out, but as long as you understand what's going into the equations, and usually, again, like I'm going to set you up with these tables, go through the little thing we're going to do next, as well as on your homework. You fill in the columns of the table and then you do the appropriate calculations. You will get the appropriate thing. The way that this most often would appear on an exam is that I might give you the equation for one of these indices and some data and say, hey, carry out the calculation, and then compare these two communities that you just calculated this for. Given this data from a Simpson's Index of Diversity, which community is more diverse? You have an understanding of how to apply your knowledge about these indices. Okay, do you guys want to try it here in class? Nod your head yes, because this is how you get participation credit. Okay, so what I'm going to ask you to do now is that everybody gets a worksheet, but you're welcome to work with people in class. We have 2 problems that we're going to do that allow you to practice calculating these indices before you get set loose on your homework later at home. So you can take out your calculator, you can use your phone. Let me know if you need a calculator in order to do these. We're going to start with the Simpsons Index. The first one, get your name on your worksheet so that you get credit in class today. Okay. When doing these, just as I've done before with our live tables, 2 or 3 significant figures is going to be plenty. when you flip over to the back, recognize that it asks again for piece of eye, and like you have that from the front of the sheet. You've already done that. You gotta do something different with it this time for the sheet. Okay, let's talk about it for a second. All right, so you filled in the table for the front sheet, the Simpsons Index of Diversity. What was the species richness? So that's going to be E, the Simpsons Index of Diversity. That's right. Okay, but for B, what is the species richness? Nope. Nope. Species richness is what? It's just the different number of species. So what is it?
5.
Not 5, but
1, 2, 3, 4.
2, 3. Is it 5? Did I?
1, 2, 3, 4, 5.
I wrote down 6, but it's 5. You're right. Thanks, Madison. All right, so off to a great start. All right, so 5 is the species richness, just the number of different species that you find. All right, in the table, you probably calculated relative abundance, piece of I, so like the first one is 2 divided by 15, you know, like the total number of individuals in the community, that species divided by that number. Okay, D, the Simpsons index, is 0.35. Okay, it's the sum of all those piece of I squares. Everybody get 0.35. That means then that the Simpsons index of diversity is 0.65, as Carl pointed out before, 1 minus that number. So relatively speaking, how diverse is this community?
Very.
Very
It's
to
okay.
medium, I would say medium to high. Remember that the range for Simpson's index of diversity is 0 to 1. So anything above 0.5, you're getting into the high range. I definitely think of 0.65 as like a medium more than like high. Like high would be 0.8, 0.9. A very skewed, uneven, single dominated species would have 0.1, 0.2 in terms of Simpson's index. Okay. The backside asks you then to calculate the Shannon index for the same data set. So what do we calculate as the Shannon index? What is the number you get at the end of all of this?
1.2.
1.2.
Yeah, 1.3, 1.2, depends on how many significant figures you carried with you. Cool. All right, how do these results compare with that of the Simpsons index of diversity? Can you compare that?
Oh. It's higher.
Sometimes this is why, 2 things here in asking this question. One is that in order to be able to evaluate it in comparison to another indices, you have to think about the range of possibilities for the Shannon index that we're calculating now for this community. So it could go from 0 to the ln of species diversity or species richness. So it can go, in this case, in this community, it can range from 0 to like 1.6 or something, the ln of 5. And so 1.3 then again is on this high range. And so based upon the Shannon index, I would say that diversity is high in this community, whereas we got kind of like a medium reading. from our Citizens Index of Diversity. That's one thing, is that in order to be able to read the Shannon Index, you have to really think about the range that's possible for that community. The second point with this question is that it's hard to compare between these two, okay? They're on different ranges, they're using the same data, but they're giving you quite different answers, okay? You know, like this one, you know, it came out to 1.3, which is above the max value for the Citizens Index to begin with. And so to be able to compare between communities and to be able to compare between researchers, you have to be calculating with the same index. And sometimes that means that you might have to go back to someone else's data and calculate the index of diversity your way, okay, in a similar fashion, because they may not have done it themselves in their paper. And this is one way where reporting the raw data then is key to continuing science. If you need to recalculate something so you can actually compare with your data, you have to have the raw data. You can't be trying to infer it from a graph or if someone's writing. It has to be there for you to actually see the raw data. Okay, whatever your indices of diversity, for this particular community, what change would be needed to increase diversity to make either of these indices higher?
More Yorkshire frog and bramble.
Good. You need to redistribute the individuals in the community so it's more even. Either of those will bump up those numbers and will make their piece of eyes and the resultant calculations with it bigger. What else could you do to increase diversity? Yeah, increase S, add more species richness. All right, what then would you do if you wanted to decrease diversity? Good, like make them have more hollow and less of the other one. Or reduce species richness, take out some species. And again, understanding sometimes the math behind the calculation then can help us understand what creates diversity in the community, and then we can manage for what exactly it is that we want. And that in some areas, we may want high species richness. And it may not matter to us that there are lots of those individuals, just as long as there's high richness. But that doesn't automatically translate to a high index of biodiversity. And so again, we have to be careful what we're talking about and comparing. We have to be knowledgeable about what we're managing for, or we're going to get something that we didn't expect, or that isn't doing what we wanted to. Any questions about diversity indices? As I mentioned, the first two problems in homework 6 ask you to calculate these two different indices for a couple communities to use to compare communities. Again, that's the next step of actually using it to compare a couple different things. So we're going to do the same calculation. Cool. All right. The next big topic for us when it comes to communities, we can count species there, we can quantify the species, we can get a diversity indices. And then from that, hopefully we have some big questions about why are those species there in the abundance in which they occur. Why is this community more or less diverse than this other one over here, given similar environments, or perhaps it's really obvious that, like, yes, they are totally different environments. Of course you're going to have totally different communities. And so one of the base questions in ecology and in community ecology is, why aren't all species everywhere and in even distribution? Or why isn't there one perfect species that dominates an individual ecosystem? And why does diversity persist? And then the converse of that, why isn't it as diverse as it possibly could be? And we're going to see that there are two major things that structure communities that cause the distribution and abundances and resulting community structure that we observe. And we have already talked about both of these things, and now we're going to take it that final step in order to build these communities and ecosystems that we live with and value. And the first huge factor in community structure are those species interactions. And they are the ones that we've talked about. Competition and predation are major community structure variables. If you have a competitor present, there's probably fewer of you. If your predator is there, it's controlling you in a density-dependent fashion, all right? And likewise, you're influencing your competitors and your predators as well. And so those interactions create communities, and they create them in very easily describable and sometimes very predictable patterns. I love this picture of the snake eating the salamander. All right, so our first major influence on community structure are species interactions, and that is population and interaction with other species will affect your population and interactions, both with each other, with those other species, and with the environment around you. And so one at the basis of lots of these species interactions, of course, are nutrition interactions. Why are species interacting with each other? They're competing for nutrition or they're gaining nutrition from each other. And so we talk in community ecology a lot about the flow of energy as well as matter within communities. And it's describing these species feeding and nutritional interactions. And the simplest of those depictions of community structure and species interactions based upon nutrition is a food chain. Hopefully you have all drawn a food chain sometime in your past. My kids did it in like first grade and I was like, this is amazing. Okay, doing ecology and algebra in first grade. There's hope for you. Again, more for freeze than for hard work, but we'll get there. All right. And so in a food chain, it's a single path of energy and matter flow within a community. We're looking at one set of interacting feeding relationships, and they have a hierarchical or a tiered interaction with each other. In all of our food chains, we're going to start with the sun that has to then feed some type of primary producer in terms of matter, carbon fixation, excess energy that is produced. That producer is eaten by a primary consumer. In this case, the grasshopper is eating the grass. That grasshopper insect is then eaten by a secondary consumer, the shrew in this case, and then that is fed upon by a third consumer, an owl. The food chain is just showing one possible flow of energy and matter through that ecosystem, something that you observed or can very accurately hypothesize from the life histories of these different organisms, these energy connections. Now, food chains are helpful in trying to figure out which organisms are predators of which, and which organisms are prey items of other predators. But they are incomplete depictions of the species interactions in a community. Okay, and so we tend to talk about food webs rather than food chains. And food chains are subcomponents of food webs. And food webs show all the feeding relationships in a community, and they attempt to do so. Very few food webs are entirely complete because there are often community members and interactions that we are unaware of. And that documenting all of the species interactions is an exhaustive and very time-consuming process. And again, based upon a knowledge of life history of organisms and similar organisms, we can often hypothesize quite well food web interactions, but it's hard to calculate all of them. Here we have lumped all of our different primary producers into the grassland ecosystem. They're fed upon by a variety of different primary consumers, all the little arrows going to different individuals. Those are then eaten by secondary consumers like our crow and our badger. Some of them themselves then act as the end of particular food resources, but then lots of them go on to higher levels of the food chain. Yeah.
When I was looking at the symbiotic relationships,
Yeah.
The badger and coyote apparently have a really odd symbiotic relationship where they will hunt together.
Oh.
And the badger will like lie in wait on one end of the burrow.
Yeah.
And then like when the coyote like starts digging, like they'll come out of the other
Yeah.
end, like the badger will get it, and then like they'll split their meal. And then they'll go and like I guess.
Totally nice.
Yeah, it's pretty cool.
Those types of feeding interactions and those like mutualisms help to complicate and fill out these food webs. And that the understanding not only that one organism can be the prey item of variety, but that sometimes these guys work in tandem with each other. and that their particular feeding relationship, whether they're a primary consumer, secondary that's eating primary consumers, or tertiary, can flow and fluctuate and change over time and space and the different community members that are present. Recognize too that it usually ends somewhere. There's like a top apex predator, a top consumer, but there is a cap on how many levels we can go up. And that for each of these movements we're going to talk about in a couple lectures, you lose some of the useful energy and matter in the ecosystem. And so you can only go so far before you run out of the calories and energy that were produced by the primary consumer, primary producers. Very often, these food webs leave out a absolutely key component, which are the detritivores, and that the recycling of matter takes place on these longer-term biogeochemical cycles, and it is accessible, and it is done by a variety of different scavengers and organisms that turn dead organisms and waste products of all these other organisms back into the base nutrients used by primary producers. And so we often show all these different kind of macroscopic organisms in our food webs, and we forget about all the microorganisms and the decomposers that then allow the cycle to continue and to keep protein. All right. Food webs are definitely these interwoven, messy kind of pictures. The last one was very simplistic, again, in order to let you actually see these interacting food chains. But they try to represent as many interactions as they can. And when we start to create food webs, we can have individual species names like in our last picture. And then we start to categorize these species, but based upon similar functions that they perform within that trophic feeding nutritional interaction in the community. And so we often talk about basal species that are autotrophs that are at the base of these food chains and food webs. We talk about intermediate species that are transferring energy and matter from our basal primary producers up higher to higher trophic levels, and then often you get to that top apex predator. And they have different jobs and different functions, and they will have different numbers of interactions with each other based upon where they lie in this type of food web hierarchy. Note that you can get interesting kind of jumps between levels in some cases, and that for lots of organisms, they self-cannibalize, and that their young or offspring or juveniles of their species are important nutritional resources for themselves. And again, this is much more common in organisms that make lots of offspring and do very little parental care, rather than species whose life history is very K-selected, where they spend lots of time raising very few offspring.
I watched the video series on Yellowstone.
Yeah.
And male black bears will eat, like
Yeah.
they're young.
Oh, yeah.
They got like 3 of them.
Yeah.
Like, so she makes them like climb up in the tree.
Yes, exactly. And so female black bears are intensely defensive of their offspring because everything will eat them.
Yeah.
Including male black bears. Okay. And so again, we think about the behaviors that we see and that we have to be aware of and careful of in these ecosystems. They're naturally selected for a reason. The same thing in lion prides. There's pretty good evidence that new male lions coming to take over a pride kill off the offspring of the previous male lions. Most importantly, to put the females into estrus again so that they can mate and have their own offspring. But then they're not competitors for their own offspring. So anyway. All right. The last thing to kind of recognize about food web interactions is that as species richness increases, as S increases, the complexity goes almost exponential. That the more species that you have in a community, the more species interactions and feeding relationships there will be. And that among these extensive quantifications of food webs in communities, we often see that there is compartmentalization, and that certain groups of species interact with each other more frequently, and they form little neighborhoods amidst the larger context of the community and the ecosystem. And sometimes these are spatial relationships that you're more likely to be predated upon and to be competing with species that live next to you. And in other interactions, there are certain taste preferences between predators There are certain evolutionary disadvantages and advantages between certain predator-prey relationships. That means some things are going to be more likely fed at home than others. Are going to be more susceptible to predation or competition. Here we see a Caribbean coral reef ecosystem food web, and they've done all of these interactions. Each of the dots is a species, and then you see all of their different species interactions, particularly again focused on predator-prey relationships. And then they started to colorize them based upon the most numerous connections between species. And so if you have lots of connections to one species, you get a similar color. And we see then that there are these groups of species that interact more frequently with each other. There are these compartments. And that oftentimes in these types of food webs, the interactions between compartments are relatively rare. They do occur, and there are some that interact more intensely with other compartments, which is kind of shown by the width of these individual ones. But the interactions within each compartment are a big component of what's happening, as much as the interactions between compartments. And so again, if we're interested in ecosystem energetics, sometimes we can simplify what's going on by thinking about compartments, or the next thing I'm going to mention, which are guilds. And this is hopefully getting you to the understanding that it's great to count and quantify everything. Okay, like that's the gold standard. But honestly, we can't. Okay, and you probably shouldn't. Okay, and that it doesn't actually help after a certain period of time to count and quantify everything. And if you start to notice patterns, that can be as important in the patterning as the actual fact of what's going on. Okay, so in these food webs, often when we have these compartments, then we can start to talk about guilds. And again, this is a grouping of trophic similarity and function within a food web or a community ecosystem. And so a guild is a subdivision of a trophic level. So again, a trophic level is this idea of our trophic pyramid, where you have kind of a pyramidal structure to biomass as well as energy within the ecosystem. There are a whole bunch of and a lot of calories and energy in primary producers. Because of the laws of thermodynamics, there's less in your primary consumers, both in abundance as well usually as biomass. And then there's even less in your secondary consumers and even less in your tertiary and quaternary consumers. And so each of these is a trophic level that have a similar function within that. Okay, and so you can call them trophic levels, or you can call them guilds. Okay, and so a guild is a group of organisms that use a resource in a similar fashion. And again, it's this idea of using a common resource. So they're in a compartment together that's all feeding on the same primary producers. Okay, so all the organisms that eat grass in the grassland community are in a guild together. They're different from the organisms that feed upon small trees and shrubs. Okay, those would be different guilds. Right, cool. Okay. Looking at guilds within a food web can often, again, be helpful in determining community dynamics as well as in management aspects. And so the realization with guilds is that you can take out a member of a guild and you'll change some of the food chains and you might disrupt food web dynamics, but there are other species that are eating the same thing and that are being eaten by the same things as a single species. And so you can lose the species, and your community will still function. It will still be there. Okay? The exact dynamics will change, but it'll function the same. If you take out a whole guild, then you really start to alter things. Then you lose lots of food web connections, lots of food chains break down. You start to see that competition and predation and prey interactions really shift dramatically. And so identifying the members of a guild sometimes is important for ecosystem management in that, again, if you have limited time and money in order to do conservation efforts, make sure you've got somebody in each guild. Okay? And that means that you might have to lose some species and be willing to let them go in the recognition that there's a replacement. Okay, the burden is shared when it comes to these types of community interactions and community dynamics. It also means that in terms of structural, for the community, losing a whole guild can dramatically restructure a community, can cause a community succession or an ecosystem shift. If you lose all of the insectivores, something's going to really dramatically change in your ecosystem. In general, what we also see from these types of analyses is that biodiversity, both in evenness as well as in species richness, tends to stabilize the community, both in the short and the long term, both in terms of energetics as well as genetic diversity, in terms of community diversity. The more species richness you have, the more evenness, the more resilient a community is to an invader. If all your niches are filled, there's no room for an invading species to come in and establish. If you're missing a whole guild of individuals due to habitat destruction, it's really easy for an invasive species to come in and establish. You've lost the resiliency of that ecosystem. And that's another huge aspect of conservation biology and the application of ecology is understanding what these connections are, and then how do we promote resiliency in these ecosystems. Species richness then also diffuses the impact of competition and predation. If there are lots of guild members, then you're all competing with each other, and there's room for you. Okay? If there are not many guild members, you're directly in competition with one other species, it might be better than you, and you'll go extinct. Likewise, if there are lots of potential food items for your predator to eat, probably not going to eat a whole bunch of you, you can persist. If you're the only thing in your guild that your predator can eat, you're going to have really high predation rates. And so again, species richness and evenness promotes biodiversity, both in terms of species richness and evenness, but then also in terms of functionality and interactions. Okay. In looking at communities, there's always a perspective that we take in these food web relationships. Notice that the species that you are focused on in your research sometimes can bias you to the understanding and the important aspects of a particular community or food web. Definitely, if you're in the predator business and you're interested in these top trophic levels, you're going to be interested in the species that feed upon and interact with things like the lynx. But you must understand then what affects those organisms that affect your species of interest. And so sometimes shifting your focus to an intermediate species can really start to demonstrate what's important in that particular community. You know, we think of the lynx as this important predator within usually cold to temperate deciduous forest ecosystems. But really, the lynx is important. There's lots of guild members. Its prey item, the snowshoe hare, has a plethora of community connections. Okay. Losing the lynx, you would lose something. Losing the snowshoe hare, you would lose a lot. Okay. So again, these food web depictions and defining these species interactions can help you identify the keystone species of a particular community. What is the one that has the most food web interactions? What is the one that if we lose or change their abundance of will impact the most of it?
Can it be necessarily like a keystone species that's not necessarily like important food web member, like the beaver?
Oh,
isn't
sure, yeah.
necessarily like a prey item that
No, yeah.
but it like is a keystone species
Oh, yeah.
because it creates different environments.
Yep, and again, that's the kind of that American alligator story where like its presence, the things that it just does during its life history, is what allows the rest of the ecosystem to be diverse, to develop as it does. You take away the actions of the beaver or the alligator, and you get a different community structure as a result. And again, it's not always feeding based. So we're talking about feeding now. Right. We're going to talk about this.
There's another symbiotic relationship of a bird that the gator will sit with its mouth open and the bird will like fly down and like take all the stuff out of its teeth.
Oh, nice. Yeah.
Yeah, and like clean its teeth so it gets a needle, but the gator gets
it's struggling. Yeah. Dental hygienist of the alligator. Exactly. Like a child, I don't think I've.
Yeah. It's a little sketchy too, but
you know, it works. It obviously works for both. Okay. On that note, let's see what's next. Okay. Before we talk about trophic cascades, does anybody else want to share their symbiosis example?
Mm.
Before Kara tells us, does anybody else have one? Okay.
Like from Planet Life or something, it was like these bats in the rainforest that would like live in this pitcher plant.
Oh.
Provide like food to the plant,
Mhm.
or, like drop waste, and
Yep.
then, but they would sleep in the plant.
Yeah. There are lots of interesting symbioses in carnivorous plants. And that again, you have these predators that will hang out in the carnivorous plant, eating some of the stuff that the carnivorous plant catches. But then their waste feeds the plant. And it's like, it's not like the plant's losing nutrition to this predator. It's actually gaining a more sustainable, reliable source of nutrition. And then they're always camouflaged, which is totally crazy.
I thought a cool one was the Colombian leatherback tarantula and the dotted humming frog. So I guess that I watched a video on this. It was kind of bizarre. I guess that this frog will go down into this big tarantula's burrow, and this tarantula is like huge. It could easily eat and devour this little frog and have a meal. But instead, the frog is more useful as like I guess it eats tinier insects that will eat the eggs of the spider.
Yeah.
So the spider just like lets you hang out. And
Yeah.
it gets like protection and like gets a shelter and protection from predators in there. And I guess like every now and then the spider will like grab him and like checking with his mouth parts.
Oh my
and then
gosh.
like let him go.
This is a nice one.
So yeah, I thought that was really, cause like I watched the video and the frog like just freezes. Like when he gets like captured, like he's just like, oh God, this is my time. And then like the spider just like lets him go and the frog just still hangs out and like, oh my God, that's traumatizing.
So it sounds like the spider's just making sure the frog knows who's in charge right now.
Yeah.
It's like, don't you betray me.
Oh my gosh, that's amazing.
Yeah, it was pretty bizarre. I thought that was pretty awesome.
Anybody else bring one in? Oh, those are great. Thank you. That gets us on the last topic for class today, which is this idea of trophic cascades, and that sometimes there are these indirect interactions. When we talk about nutrition and trophic webs, we're talking about direct feeding relationships. But this idea of mutualism bypasses some of these levels. We have these interactions between species that we may not anticipate and that may not be obvious from just food chains. And so the Yellowstone ecosystem is a particularly interesting case study in this with the reintroduction of wolves. And in trophic cascades, it's this idea that predators indirectly impact autotrophs, and that this is the secondary, tertiary, quaternary level predator that does not themselves eat plants, influences plant diversity and abundance by eating herbivores. And so again, we have this indirect interaction between this. We can notice that when there's lots of browse, then snowshoe hares increase. As snowshoe hares increase, then their predators increase. When the hares begin to overgraze, then their population starts to decline, both because they have less food, and then also because their predators have increased in abundance. And that predation control of the hares causes them to collapse, and then their food resource can rebound. And so this predation impact on the hares affects the availability of the autotroph and its abundance, which then allows for the restart of the cycle as the predators then crash from their prey. And these are really cool interactions to start to appreciate and recognize, and they're often stuff that we would not know about unless we were really looking at community ecology. If you were just doing food web interactions, you may not be able to put all of this together. So I'm going to give you just a little bit of information that's coming out of Yellowstone with this reintroduction of the wolf population. Here in North America, we lost all of our really large predators from the late 1800s through the early 1900s. We really saw these big predators as competition for a livestock resource. Now, we wanted to graze more livestock. We wanted to hunt the herbivores that were out there. We needed to push out the other major tertiary consumers other than ourselves. And so we killed them all. They went away. And then the ecosystem has changed dramatically as herbivore abundance has rebounded with the loss of this predation pressure. We as humans initially were providing enough predation pressure on these natural herbivore populations because we hunted and fished all the time to control them. And as we moved away into modern agriculture and urbanization, we quit harvesting as much. And these herbivore populations have just boomed in recent times. And so in the kind of mid-1990s, we reintroduced wolves into the Yellowstone ecosystem. And we've seen some really interesting effects on Yellowstone in ways that we didn't anticipate from the reintroduction of these wolves. And so we certainly anticipated that wolves would eat elk, which they do. That's great. What we didn't expect was that the vegetation would change dramatically with the loss of the elk herbivory. And so here in this instance of the wolves eating elk, it has really affected aspen growth and availability, which then has impacts on other organisms. And so we have a predator that's eating its prey, the wolf eating the elk. As the wolves increase in abundance, the elk decline in abundance. And that affects the prey of the elk. Okay, and so again, we see that in two different kind of regions here by stream beds and then in the upland kind of prairie ecosystems. As the elk decline, the percentage of the aspens that are browsed by elk also decline. Okay, totally expected. But you may not be thinking about that when we introduce wolves. We're just thinking about the impact of them on their individual prey, but it has a downstream effect on the rest of the trophic pyramid. Again, as there's less browsing, the height of the aspen trees increases. Cool. What's also interesting is that the amount of predation by the wolves has an effect on the aspen trees. And so in areas where there is a low risk of wolf predation, the percent of the aspen trees that are browsed remains quite high, and the height of those aspen trees is 10 because they're getting eaten by elk. But even if there's a high risk that you might be predated upon by an elk, that has an impact on the trees. And so in these high-risk sites where it's more likely that you're going to be chased by a wolf and then perhaps caught by a wolf, we see that the browsing on the aspen trees really declines. As a result, they grow a lot taller. So again, even the threat of predation, not the actual change in abundance of elk, is enough to cause this ecosystem shift. And it has been an ecosystem shift, that as the aspen trees and other trees have regrown, then we see a diversity of other organisms that had previously been absent when those trees were not in that ecosystem. They come back to the ecosystem. It's different today than it was before wolf introduction, even though we have changed one species. Cool. And some of those examples of these indirect feeding impacts of the wolves, again, the predator eats its prey. It indirectly affects not only the prey's prey, the aspen trees, but then these other compartments, these other kind of guild members. So we see that there's this connection between wolves and elk and aspen trees and bears, as well as songbirds, at least in Yellowstone Park. And what we're seeing is that the wolf eats the elk. And so there are fewer elk with eating, which means that there are more berries available on the berry-producing shrubs in Yellowstone. So not only is the elk eating less aspen seedlings, they're also eating fewer berries. And this means that there are more berries available for grizzly bears to eat. The competitor for the berries was the elk. As elk competition goes down, the bears eat more berries. And we see that as the number of elk is very high, the percentage of fruit in the bear diet is very low. As the elk are reduced by wolf predation, there's more berries in the bear diet, which is, I would not have anticipated that, but it's very clear that it's related to wolf predation. The same thing in songbird diversity. The elk not only have browsed back on the aspen trees, but they've really affected willow tree growth along these stream and freshwater streams in Yellowstone Park. It's one of their preferred areas to browse because they have easy access to freshwater as well as to grazing. And so we see that as the elk are reduced, the willow trees grow back, which is this released willows bars here, and we see that the richness of songbirds has increased, and that the Shannon Weiner diversity indices has increased as well when you have wolves introduced. So wolves don't eat songbirds, but they have an impact on their diversity, both in presence absence as well as in kind of diversity indices evenness as well. So these food web interactions that help structure communities, what species are there and what abundance depends upon these types of feeding relationships. Okay. Cool. We will pick up here as we talk about top-down interactions and then bottom-up interactions in these feeding relationships. Is like, what's most important? Is it predation or is it the primary producers that are there to begin with? And so there are these two different things that can be structuring communities in terms of nutrition. And we'll see that there's evidence that both can be important. Cool. Okay. I'll see you in lab tomorrow. Thank you.
Do you want the papers?
Oh yes, I love your diversity indices paper. I'll give you